All right, so let's get started on today's meeting. So what we're going to be doing today is we are going to be wrapping up our look at Chapter 9, Conceptual Knowledge, by finishing our look at Connectionist networks. So we started that last time. Today is going to be part 2. And what we've been exploring is the idea of how is knowledge represented in the human mind. And one of the representational strategies or representational theories that we have about what is going on in the human mind is that knowledge is represented not as a series of propositions, but as a series of connections of differing weights and differing directions and connections between differing ideas, concepts, and nodes. And that is what allows us to do our cognition. And further than that, some of these connections, we don't even have concepts that they code for necessarily, but basically they do the work of cognition by having that interconnected architecture that allows inputs to go from an input layer through a series of really complicated, interconnected transformations and allows us to get to an output layer. So we introduced the idea of connectionist architecture last time and mentioned that this is the architecture that has given us the ability to finally crack some of these really difficult computational problems that we had, such as how do you make an automated driving car? How can you make a large language model that can actually pass the Turing test and mimic, at the very least, mimic human speech, human thought, human writing? And then also, how can you do things that are usually thought of in the realm of just creativity in humans, such as making videos? How can we do that computationally? All of it is being implemented by these connectionist networks. So the fact that we can achieve these very human-like things with connectionist networks gives us hope and some evidence and some likelihood that maybe this is actually how we achieve it as well. So what we're going to be doing today is we are going to start with just a real quick recap about knowledge representation. And then we're going to go into some connectionist networks. We're going to see one for number recognition and how it's implemented. We're basically going to show how that same architecture can be used to represent animal knowledge, for example. And then we're going to take a look at an example where this programmer used the connectionist architecture, connectionist network, to program a computer to play Super Mario World better and better and better. So the first example that we're going to take a look at, the number recognition, this is from 3 blue, 1 brown. And we're going to take a look at, as part of our quick recap, how this is set up to recognize the different numbers. So how this is set up to take input, visual input, in this case in the form of a bitmap file, take that input and then run it through this connectionist network and create an output that we can then interpret as to whether or not the connectionist network made the correct decision of what number was presented. So this is the basic build for any connectionist network. And what we have here is we have our input layer. And the input layer is where the information enters the connectionist network. So this one here has 784 nodes that are your input layer. And that comes from 28 times 28 being the resolution of the image that was put into the program here. So we have 784 nodes that turn on if the pixel is white and turns off if the pixel is black. So if the pixel is white, that node turns on, sends its signal. If it's black, that node does not turn on, does not send its signal. We also have an output layer in our connectionist network, and this is where we finally see what the decision is. So in this output layer, this is where the decision is made, and basically the output node with the highest activation is the one that gets chosen as that is what this connectionist network saw. And in this case, you can see that 5 is the highest activated node. So in this case, the network would make the decision that, yes, I saw the number 5. So we have our input layer, we have our output layer. Very importantly, we have our hidden layers. So the hidden layers are the connections that do the magic of the cognition in a connectionist network. And you can have any number of hidden layers. In this case, we have 2 hidden layers. And importantly, those hidden layers are connected to the input layer. They're connected to each other, and they're connected to the output layer by these different connections. And those connections have different values in terms of they're either a positive connection or a negative connection. So in this case, blue connections are positive connections. That means if a node fires and it's connected to a second node with a blue connection, that node will send activation to its second node. It will increase the activation of that second node. However, if it's connected via a red connection, then it will decrease the activation of that connected node. And the more bold these connections are, the stronger they are. So a bold connection either sends a very strong excitatory signal or a very strong inhibitory signal, and a less bold connection sends a lower excitatory or lower inhibitory signal. And we saw how in a very simple connectionist network, you can actually code, without coding the propositions, you can actually represent the knowledge of the exclusive disjunction, meaning that you can have X or you can have Y, but you can't have both, but you need to have one. So again, we saw that this can, through activation and through these connections, come to the correct decision that if you have X, yes, you have followed the rule. If you only choose Y, yes, you have followed the rule. If you choose both X and Y, no, you have not followed the rule. And if you don't choose either, also no, you have not followed that rule. So that's a very simple model that we just went through and kind of ran through. But this is the basic idea of what is going on in connectionist models. So you can have more complex connectionist models. So for example, we could create a model that represents our knowledge of living things. And if we were to do this in a list representation, then you can imagine we would have things like birds can fly, birds lay eggs, birds have feathers, birds can move voluntarily. And then we have another category for fish. Fish lay eggs, fish live in water, etc. We can put it in a list representation, but we can also model this knowledge in a connectionist network. And as it turns out, the basic idea of this is pretty much the exact same, where in this case, you would have an output layer, and this time the output layer would be the different categories of living things with one category for non-living things. So you would have things like, well, we got mammals, we got birds, we got reptiles, we got amphibians, we got fish, insects and arachnids, plants, fungi, microorganisms, and then non-living things. And then on the input layer, you have something like has fur or hair, can fly, lays eggs, is warm-blooded, so on and so forth. So what would happen in a connectionist network like this is that those input layers would get activated, and then through that processing of being connected to those hidden layers with strong versus weak connections, with excitatory versus inhibitory connections, what it would do is it would activate and process all that information and come out the other side. One of those 10 categories, mammals, reptiles, insects, and arachnids, would be activated the most. And then that would be the decision that this network would come to. So in this case, it would come to the decision that, yes, it was looking at either an insect or an arachnid. And that would be one way to represent a connectionist network of everything that we know about different animals. All right, so those are the connectionist networks, the ideas of a connectionist network. These are models of how knowledge is represented. They're known as parallel distributed processing or PDP models. And the reason for that is because this information is processed in parallel. So all of the input nodes send their information at the same time. All of those hidden layers send their information at the same time. all of the output layers get that information at the same time. So it's working in parallel, not in serial. And that is one of the reasons why we can do so complex computations, because the computing power of this is just absolutely massive. Whether you're looking at how you recognize numbers, or whether you're looking at how do you make decisions about what animal you are looking at based on, or what living thing are you looking at, or are you looking at a living thing based on, does it have a backbone, does it have roots, does it produce spores? All right, so let's take a look at how this might actually be implemented, and how these are actually built, and some of the more technical aspects of it. I promise we won't get too technical, but let's take a look at how this could actually be programmed. And as you'll see, human beings don't really program these parallel distributed processing networks. They don't really program a connectionist network. What they do is they set it up, and then they have an algorithm by which the network will learn what connections need to be done. So without further ado, I turn it over to do 3 blue, 1 brown for that explanation.
In either case, right now, all we're going to do is focus our attention on one single example, this image of a 2. What effect should this one training example have on how the weights and biases get adjusted? Let's say we're at a point where the network is not well trained yet, so the activations in the output are going to look pretty random, maybe something like 0.5, 0.8, 0.2, on and on.
Okay, so first off, you can see that at this stage, as he mentioned, the network is untrained. Basically what that means is you give it an input, and the output that it gives is wrong. It gives the wrong answer. In this case, it's saying, well, I'm looking at a 3 or I'm looking at a 6, while you're actually looking at a 2. So this is part of the training. And now let's take a look at how that's going to change the connectionist network.
Now we can't directly change those activations. We only have influence on the weights and biases. But it is helpful to keep track of which adjustments we wish should take place to that output layer. And since we want it to classify the image as a 2, we want that third value to get nudged up, while all of the others get nudged down. Moreover, the sizes of these nudges should be proportional to how far away each current value is from its target value. For example, the increase to that number 2 neuron's activation is in a sense more important than the decrease to the number 8 neuron, which is already pretty close to where it should be. So zooming in further, let's focus just on this one neuron, the one whose activation we wish to increase. Remember, that activation is defined as a certain weighted sum of all of the activations in the previous layer, plus a bias, which is all then plugged into something like the sigmoid squishification function, or a ReLU. So there are 3 different avenues that can team up together to help increase that activation. You can increase the bias, you can increase the weights, and you can change the activations from the previous layer. Focusing just on how the weights should be adjusted, notice how the weights actually have differing levels of influence. The connections with the brightest neurons from the preceding layer have the biggest effect, since those weights are multiplied by larger activation values. So if you were to increase one of those weights, it actually has a stronger influence on the ultimate cost function than increasing the weights of connections with dimmer neurons, at least as far as this one training example is concerned. Remember, when we talk about gradient descent, we don't just care about whether each component should get nudged up or down, we care about which ones give you the most bang for your buck. This, by the way, is at least somewhat reminiscent of a theory in neuroscience for how biological networks of neurons learn, Hebbian theory, often summed up in the phrase, neurons that fire together wire together. Here, the biggest increases to weights, the biggest strengthening of connections, happens between neurons which are the most active and the ones which we wish to become more active. In a sense, the neurons that are firing while seeing a 2 get more strongly linked to those firing when thinking about a 2. To be clear, I really am not in a position to make statements one way or another about whether artificial networks of neurons behave anything like biological brains, and this fires together, wire together idea comes with a couple meaningful asterisks. But, taken as a very loose analogy, I do find it interesting to note. Anyway, the third way that we can help increase this neuron's activation is by changing all the activations in the previous layer. Namely, if everything connected to that digit 2 neuron with a positive weight got brighter, and if everything connected with a negative weight got dimmer, then that digit 2 neuron would become more active. And similar to the weight changes, you're going to get the most bang for your buck by seeking changes that are proportional to the size of the corresponding weights. Now, of course, we cannot directly influence those activations. We only have control over the weights and biases. But just as with the last layer, it's helpful to just keep a note of what those desired changes are. But keep in mind, zooming out one step here, this is only what that digit 2 output neuron wants. Remember, we also want all of the other neurons in the last layer to become less active. And each of those other output neurons has its own thoughts about what should happen to that second to last layer. So, the desire of this digit 2 neuron is added together with the desires of all the other output neurons for what should happen to this second to last layer. Again, in proportion to the corresponding weights, and in proportion to how much each of those neurons needs to change. This right here is where the idea of propagating backwards comes in. By adding together all these desired effects, you basically get a list of nudges that you want to happen to the second to last layer. And once you have those, you can recursively apply the same process to the relevant weights and biases that determine those values, repeating the same process I just walked through and moving backwards through the network.
Okay, so you can see just absolutely how massively complex this is going to be. So if you have 10 output nodes, and each of those 10 nodes is connected to 10 other hidden layer nodes in the layer just behind it, you're going to have to make 100, more than that. You're going to make 200, because you can adjust the weights and you can adjust the activation. You're going to make 200 changes potentially to those connections. Take that back another layer where now you have another 10 connections. So you have your 10 connections connected to another 10 connections, and you can do those. But you can do the activation, you can do the weights. You're going to take that 200, you're going to multiply it by another 200, and now you're going to end up with 4,000 potential changes that you can make. And that's just going back one more layer. Now you got to keep going all the way back, and you can see how complicated this potentially can get. But importantly, this is an automated system that is built into the model. So this idea of backwards propagation is an automated system that is built into the model. So all you need to do as a programmer, as a person that is creating this connectionist network, is let the network know whether the decision it made was correct or not. So if you gave it a 2 and it says, oh, I saw a 3, all you need to do is say, no, that was a 2, and then let this backwards propagation change all the weights and continually train your model. And that is exactly what they do when they're developing automated driving systems, for example. So you have basically the connectionist artwork is all set up. There are other programs that deal with getting the inputs from the road, for example, for recognizing what is a pedestrian, what is another car, what is a sign, for dealing with apparently ways that people sometimes try to hack the system. So I have heard that automated taxis have some trouble with people taking construction cones and just putting it on top of their hood, and then the taxi will never move because it doesn't understand that this thing is not going to get out of its way. But anyways, you take it through a whole bunch of trials and basically indicate when it's getting things wrong, when it's getting things correctly. And then through that back propagation, it will adjust the weights and get continually better and better and better and better at making the right decisions, making the right discriminations. Before we leave this idea, I just want to mention a few things that three blue, one brown mentioned, which was that this in many ways mimics how humans learn as well. So if you think about how you might teach a child the numbers, you basically show them the numbers, and then you say, well, what do you think this is? And if you're showing them a 3 and they say, oh, that's number 2, then you tell them, no, this is actually a 3. And then through some process in their mind, they will adjust the weights of what they were input and what they output, so that the next time they're more likely to say a 3 when they actually see a 3. So many of the things in a connectionist network work very much like how a human mind actually works. So some of the learning patterns that you'll see if you deal with connectionist networks mimic how children learn things. So, for example, in language, children have a tendency to learn the exceptions to certain conjugated verbs first. And then when they learn the rule, they overgeneralize to those exceptions during that period. So, for example, if you teach a child that the past tense of run is ran, in the beginning, they will, or early on, they will say, oh, yesterday I ran to the park. And you will tell them, yes, that's very good, that's very good. But then they learn that you add ed to the end of verbs. So they'll learn, oh, I jump today. So yesterday I jumped. And you'll be like, yeah, that's very good. And I'm trying to think of another one that isn't. So I'll just stick with the one example because my connectionist network is failing me right now. So they will learn, oh, what you do is you take that verb and you add ed to the end. So it was I jumped. Yesterday I jumped. What they will do is they will overgeneralize that. So there will be a period where they stop saying, yesterday I ran to the park. And instead they'll start saying, yesterday I runned to the park. And they'll say, yesterday I swinged on the swing set instead of swung on the swing set. So they will overgeneralize. And then eventually they will learn, okay, I can apply this rule to most of what I want to say in the past tense, but there are some exceptions like ran that I need to make special note of. That exact same thing happens to connectionist networks when they're trying to learn language. They will learn the exceptions to verbs, they will learn the rule, and then they will overgeneralize and say things like, I run to the park, much like a child learning language. So there are a lot of similarities between how connectionist networks do cognition and how humans do cognition as well. And incidentally, one of the most interesting things that you can do with a connectionist network is you can impair them and then see how those impairments reflect in the behavior. So you can literally start going into a connectionist network and start cutting connections and say, all right, I'm going, or deleting entire hidden layer nodes and see what the impact of that is on your cognition. And what you will see is you will see a degradation, a deteriorating that is very much like what happens when humans suffer certain impairments in their cognitive abilities. So when we were taking a look at semantic networks a few classes back, and we did the thing about, well, you know, what if somebody could incept into your mind and they change your Lincoln node, your Abraham Lincoln node from Lincoln to Bill Gates? And we went through that example, and one of the questions in the class came that, well, would you completely forget what you knew about Lincoln? And the answer was, yeah, you would. If Lincoln was represented in that one node in your semantic network and you swapped it out with Bill Gates, everything that you thought you knew about Lincoln would be gone and it would be replaced with Bill Gates. That doesn't happen. And the reason it doesn't happen is because your ideas and your knowledge representation of Lincoln looks more like this. And if you get some impairment in this network, some of the things you remember about Lincoln will be gone, but not all of the things that you learn about Lincoln will be gone, because Lincoln is not stored in a single place, but Lincoln is stored through a series of connections. And you might lose some of those connections, but you wouldn't lose all of the connections typically. And that's why you don't all of a sudden forget who somebody is. You might forget certain things about them, but you don't forget the entirety of what you knew about that individual. Mm-hmm. You know, that's a really interesting question, because I wonder that same thing as well. I mean, people must have had the experience where they disagreed on what actually happened. And either you could go back and verify, or you could logically understand that one of us is wrong, right? And one of us is misremembering something. I would think either for a vast period of humanity's existence, we did not have the ability to really go back and verify. So it's only recently that most of our lives is documented in some verifiable way. So it could have been a symptom of that. It could have been a symptom of people not really noticing it and its implications in terms of what is actually going on. And it really, we're going to see this later on today when we talk about when we talk about problem solving. But the last reason I think is that oftentimes people come up with an idea of how things work, and then they just apply that idea everywhere and ignore the counterfactual evidence to maintain the integrity of that overarching simple idea. So there is a large history of people getting things wrong and holding on to those wrong ideas until just overwhelming evidence came by and refuted it, or maybe the right person came by and refuted it. So one of the ideas that I can't remember exactly when this was abandoned, I think probably like in the Victorian ages. One of the ideas was that children are basically miniature adults, and you just got to pour the knowledge into them, and but their brains work the same as our brains, their emotions work the same as our emotions. They're just these little mini adults that you need to socialize and you need to impart knowledge to. That is, I mean, anybody with a child that spends 10 minutes with a child will tell you they're not little adults. They are children through and through, and that's a very different entity. It's not just a difference in what you know, it's a difference in how you think, it's a difference in how you experience the world. But you would think that that would be self-evident, but for the longest time, people thought, no, that's just, they're little adults and that's how we're going to treat them. So I really don't know sometimes how things stay unseen for so long, but I know that we're not immune to that either. And there are going to be things that come up, and there's going to be discoveries that are made, and there's going to be shifts in cultural knowledge that we all have. And afterwards, we're going to take a look back and we're going to think to ourselves, how could we have not seen this coming? Or how do we not know this? And we're going to be in that exact same position. So there have actually been, if you're interested in this, there have actually been studies done on ideas that are related to this in terms of warnings that were ignored for catastrophes that later occurred. So these are things that have been documented where people have either sent emails about, well, this oil rig has a faulty system and we're like, months away from a huge oil spill. Or we have this intel coming from certain terrorist organizations and we're a couple of weeks away from, some terrorist attack and these things were just ignored. And it's a very similar idea. Why was this information not taken in and used to make different decisions? It's a kind of open question in terms of our cognition and how our brains work. And it might actually be something to the effect that maybe we are processing this information, but we have these connectionist networks that are so ingrained already that one example going through it, it'll nudge the weights a little bit, but not very much. And once it's gone through the network, it's done its work. So maybe we just don't think about it that much anymore. Yeah, it would be what a world we could live in if we were way better at seeing things in the way that they actually were. And we were able to take counterfactual information and say, I need to update my basic assumptions or my basic theories rather than I'm going to find a way to ignore that. And maybe one last thing that I'll mention, just as a sort of aside, because it just kind of popped into my mind. Stephen Hawking, the physicist, he was once asked, why didn't Albert Einstein realize that they were black holes? So literally, most of theoretical physics, most of astronomy, um, is still working on the equations that Einstein came up with. And they're like, well, if these equations are true, then this should be true. And they look out into the world and they're like, oh my gosh, it really is true. Well, one of the big, huge things that was predicted using nothing but Einstein's equations, but Einstein didn't do it, was the idea of black holes. So somebody once asked Stephen Hawking, because Stephen Hawking was like the black hole superstar. They asked him, well, how come, you know, uh, Einstein didn't notice these black holes? And Stephen Hawking's response was, you can't notice everything. Like you can't think of everything. So it's just, yeah, sometimes it's there, but we just can't see it. And I guess sometimes collectively as a culture, the same things occur. Any other questions about the connectionist network and back propagation? All right. So the last thing that we're going to take a look at for this connectionist network way of representing knowledge comes from Seth Bling. And what he did was he created a connectionist network to teach this program how to play Super Mario World. So we're going to go through a little bit of his teaching of that system, just again to see how these different connectionist networks can be implemented to do things that are very human-like behavior. Oh yes, so Super Mario World. And one of the things that I'll just mention is that little gray square in the top left there, that is the input that is being given to the first layer of this connectionist network. So each one of those you can imagine that gray square is split up into a whole bunch of little squares. What is active, what is present in those little squares is basically what is being input into the computer. So you can see those white squares at the bottom. That is what Mario just jumped off of. And you can see that red up and down line. That is one of the coins that you can see on the screen there, I believe. So that is the input. Those controls over there on the right, that's the output. So press A, press B, press X, press Y, move up, move down, move left, move right. That is your controller. And basically, he built a connectionist network to go from the input of what is on the screen to the output of what your move should be.
Welcome back, Seth Bling here. You're watching a skilled player play Super Mario World, but this player is not human. It's a computer program I wrote called Mar.io. This program started out knowing absolutely nothing about Super Mario World or Super Nintendo's. In fact, it didn't even know that pressing right on the controller would make the player go towards the end of the level. It learned all of these things through a process called neuroevolution. In this video, I want to teach you about how Mar.io learned to beat this level, Donut Plains 1, what his brain looks like, and how it's all based on actual biological evolution. So let's start out by actually looking at Mar.io's brain. Let's play it again, but this time we'll look at Mar.io's brain as it's making the decisions of what buttons to press. It's going to look a bit complicated at first, but don't worry, I'll help break it down for you. This structure of colored lines and blinking boxes is called a neural network. It's a simple mathematical model for how a brain works, but it can produce some very complicated behavior. With enough computational power, a neural network could come close to simulating a real human brain, but modern technology isn't there yet. On the left side you have the inputs. This is what Mar.io sees. It's a simplified view of the level. The white squares stand for blocks the player can stand on, and the black squares stand for moving objects like enemies or mushrooms. On the right side you have the outputs. These are the 8 buttons that Mar.io is able to press by using its neural network.
Just real quick, I was wrong about that red line in the center of the square there. That's actually where Mar.io is in the input.
In between the inputs and the outputs, all those lines and boxes, those are the neural network. Each free-floating box is called a neuron, and the lines connecting those boxes are like the axons and dendrites in a human brain. At any given time, only some of these neurons and connections are actually being used, and this is what people talk about when they say you only use 10% of your brain. The neural network you're seeing is a pretty complicated one, and it got so complicated as a result of a 24-hour evolutionary learning session. So, to explain how neural networks work, let's rewind about 24 hours and look at how the whole process started. This is what Mario looked like at the beginning of its training session, all the way back in generation number 0. The program is probably even dumber than you thought at this point. Often it just stands there and doesn't even press any buttons. If Mario stands still for too long, it'll cut off the simulation and try the next neural network, so it's mostly just jumping from one simulation to the next. But occasionally, the neural network says to press the right button, and the player starts walking right. The behavior isn't complicated, but it's enough to make at least some progress in the level. Let's take a look at a sample neural network to understand just how that works. This is one of the randomly generated neural networks that appeared in the first generation of the simulation. There are some green lines and a red line, and one neuron in the middle. Here's how it works. A green line is a positive connection, and a red line is a negative connection. A green line reading from a black or white square will turn its output the same color. A red line reading from a black or white square will turn its output the opposite color. In this case, the green lines read from the platform that the player is standing on and make the neural network press the right button as long as the player is standing on it. However, when the red line reads a black square representing one of those caped Koopas, it presses the A button and makes the player jump. This puts the player in a position where the green lines are no longer reading a white square, so the right button turns off and Mario just stands there. This is a really basic example that illustrates how a more complicated neural network might operate. The more lines and neurons you have, the more nuanced the decisions can be. So, how exactly do we get those more complicated neural networks? The answer is evolution. When Mario gets further right on the screen, its fitness goes up. In this case, fitness is a function of how far right it gets and how quickly it gets there. Only the neural networks that produce the highest fitness are selected to be bred, creating the next generation. It took 34 generations of genetic breeding and fitness evaluation before Mario was able to finish the level without dying and get a fitness score above 4,000. You can see there were several places it got stuck for a few generations, but it always evolved out of those ruts. Let's take a look at a few of those ruts. You can look at the top left corner of the screen to see what generation number each rut occurred on. This process of picking the fittest individuals from each generation, breeding them together, and adding random mutations very closely matches the actual process of biological evolution that took single-celled organisms and produced intelligent humans. That's the power of neuroevolution. And though we don't yet have enough computational resources to produce something on the level of a human brain this way, it's kind of neat to see what it can do on one of my favorite games. I didn't come up with this idea on my own. This algorithm is called NEAT, which stands for Neuroevolution of Augmenting Topologies.
All right, so we'll stop on the video there, but just again a few examples here. Number one, he started off with just random connections. So you start off with a model that is just made randomly, and it says just randomly press some buttons, and you don't even have to program in basic knowledge of, oh, press the right button and it goes right, press the left button and it goes left. And eventually those random button pressing will lead to progress, in this case defined as a higher fitness, and then whatever led to that higher fitness will then be back propagated so that its connections get strengthened, and anything that led to lower fitness will be back propagated so its connections get less strengthened, and eventually you end up with a connectionist network that can play the game, finish the board, and do it oftentimes in very unique ways. So we're not going to have time to talk about one of the problems in, or the big concerns in AI, which is the problem of whether or not our sub-goals match the sub-goals of an artificial intelligence system. But we could see some of those here, some of those discrepancies here in this example. So for example, when you were watching this, if any of you have played Super Mario in the past, you might be screaming at the screen, you know, go get some of those coins. You're missing all the coins. You might have been thinking to yourself, well, jump over that projectile. That projectile is coming at you, and you're going to lose your, you know, your giant size after consuming the mushroom. Computer, this program didn't care about any of those. Didn't care at all about those things because they weren't sub-goals that aligned, that's the word, the alignment problem. They weren't sub-goals that aligned with what its end goal was. So in this case, in this Mario game, we have an artificial intelligence connectionist network that is solving this board in a way that human beings would not solve it, indicating that its sub goals did not align with our sub goals. Doesn't mean that its solution is not as good, maybe even better than our solution, but it is concerning that this oftentimes occurs when we ask AI to solve problems. So another famous example was AI was trained to play Space Invaders. So Space Invaders is that game where you have the Space Invaders and they're like, and they get to the end and then they're like, they fall down and you got to shoot them. And you start off with 4 bases that you can hide behind in case one of the aliens shoots a projectile at you. Humans typically will maintain those 4 bases for as long as they can and play the game and try to hide away from the fire when it's coming down. They'll use the bases to their quote unquote advantage. When these computer programmers made a connectionist network that played Space Invaders, they let it run for 24 hours. They basically set it up to automatically learn. They went home for the night. They came back in the morning. And this computer was not only an expert player, but one of the first things that it did was destroy its own bases, because those bases just got in the way of it being able to go on offense and wasn't very useful to the computer for defense. So something that most people would have never done, this computer decided, you know what, these bases, they're an obstacle. We're going to destroy those bases so that we can get to the aliens. So once again, this strategy that humans typically would not have come to that decision. And then the last example that I'll give, this one was one that I recently saw on a video. It was a very humanoid robot that was being trained as a caretaker, somebody that can, prepare dinner, walk the dog, fold laundry, things like that. So one of those humanoid computers that are humanoid robots that hopefully will be a sort of like generalized intelligence that can help out with people who need that kind of assistance. So this robot was cooking eggs. And the person who was training the robot gave it an egg and asked it to determine, is this egg hard-boiled or is it raw? And the way that the robot determined that was to just break the egg on the counter. And sure enough, yeah, the answer is, yeah, it was raw. But again, not how a human solves that problem. And one of the concerning things is, what other eggs are AI willing to break that we have not explicitly said, do not break these eggs? I mean, whenever you look at a villain, if you want to establish that somebody's a villain in like a story, one of the phrases that you can go to is that you can't make an omelet without breaking a few eggs, right? So they just murdered their entire team in order to achieve their goal. And somebody tells them, well, what did you do? You killed them all. And they're like, well, you can't make an omelet without breaking some eggs. Well, you can't figure out if an egg is hard-boiled or raw unless maybe you break some eggs. Again, it's not things that occur to humans. We have these sub-goals that we typically all agree on. And one of the big issues with AI is this alignment problem of whether or not AI sub-goals will align with what we have, or do we need to explicitly make those programmed into the AI, and then will it eventually, even just ignore them? So any questions or anything before we leave connectionist networks and turn to our next topic? Yep. Oh, good question. So the question is, if you so basically you start from a new model, start from scratch, and you retrain it, and will it be the same every single time? The answer is no, absolutely not. So definitely 100%, if you start with a model that's randomly connected, right? So you have the same architecture, but you just put in the random weights and the random activations, and you train that model on, let's say, 10,000 trials, and then you redo it, random model, train it on the same 10,000 trials, you will get different models. They will still be pretty much equal in performance, probably the same way that all of us have different models in our connectionist brains, but all of us learned the alphabet, all of us learned basic mathematics. So it will be pretty much the same performance-wise, but it will be completely different in terms of what the connections are. Now, if you start with the same connections, so instead of starting with two different random configurations at the beginning, you start with the same random configuration at the beginning. Then from what I understand with backwards propagation, you should end up with the same model. And once you have that model, then you can duplicate it, right? So you can take all the weights and all the connections in a particular model, and you can say, all right, put that one into this next model, and put that one into this next model. And that's how, if we ever do crack general intelligence, we could have this connectionist model of general intelligence, and we could say, well, let's put that into this robot, let's put that into this robot, let's put that into this robot. You can duplicate that. But it is interesting that you're not going to end up with the same connectionist architecture or the connectionist weights and activations if you start with two different random models, even if they're trained on the same information. And that is basically how our brains work, because what your brain does when it's developing, your brain is typically has the most neurons and the most connections by the age of 2. And then what happens is it goes through pruning, where you find out that all of these random connections that your brain came up with, that it basically built this entire connectionist network. Most of those you don't need. Most of those are not useful. Most of those are contradictions, and they just never fire, so they die out. You go through pruning, and then you end up with your brain that is necessary. And that is a lot like what happens with connectionist networks. It could, yeah. I mean, it could solve it quicker. It could be quicker. It could be longer. It really depends on what is that random thing that occurs. Remember the variability that he was saying? Well, we mixed in variability on every single on all these different trials. What is that variability? Is it useful variability or is it not useful variability? So it's almost like you can imagine if you were playing a game against somebody and you were rolling dice and you got to move ahead every single time you rolled a 6, but if you roll anything else, you have to stay where you are. Eventually, somebody is going to be way out in front because they just by luck rolled a whole bunch of 6s, early. Other people are going to be way behind because they just aren't rolling any 6s. So on average, everybody's going to move at the same pace, but some people will be way far ahead and some people will be way far behind. So with connectionist networks as well, some networks will learn much quicker, others will learn much more slowly. One of the interesting things, though, and this is also true of humans, is that the more the more learned a network is, the more able it is to learn additional things. So that Mario game took, what was it, like 35 generations before it could complete that level. If you now go to the next level, something it's never seen before, something it's never been trained before, it will learn that next level way faster than if you just started from scratch again. And the reason is because it has all those basic rules and basic strategies programmed into it now in that distributed parallel processing model, so that it can actually build on that. And that's typically what you see with human behavior, that if you learn something, you can then transfer a lot of that knowledge to other domains. So if you're a good video game player, the next video game you try to play, you're going to be way better than most people. If you've learned 4 languages, you're going to learn that 5th one a lot quicker than somebody learning their second language. Those types of things are, again, things that we see in connectionist networks and also in human beings. Any other questions or comments? All right. So we are going to move on from connectionist networks now and conceptual knowledge